So today we will have another tutorial session on the principal stresses. So the first problem. So here is a small element chosen from a component. The components of the stress acting on the elements are given. The X component is 120 MPa, Y component is 90 MPa, and shear component is 30 MPa. So we are expected to compute the stresses on an inclined plane, which is inclined at 20 degree, and determine the principal stresses and their location, that is their orientation, plane, principal plane, okay, and maximum shear stress and its plane, okay. So since theta is straight away given, we can make use of the principal stress equation involving theta, okay. So here is the equation with theta, maximum principal stress equation with theta, okay, sigma theta. So cos 2 theta and sin 2 theta, you please substitute that in degrees itself and you will get the maximum principal stress. And shear stress, we also have the corresponding equation while we derive stresses on inclined planes, right? These are derived in mechanics of solids itself, so please remember them. It is matter of substitution. So it is minus 13.34 MPa. It is a 20 degree plane, on a 20 degree plane. So these two expressions are the expressions for stresses on inclined planes, okay, when they are subjected to biaxial loading and as well as shear loading. The next part is we need to determine the principal stress. So that we already have the direct expression. You just have to substitute it. Okay, sigma 1 maximum principal stress, minimum principal stress, only plus and minus here is the difference in these two equations. These are the magnitudes of the principal stress. Coming to the this orientation or location or plane, principal plane, right? So we have that equation, half of tan inverse of 2 tau by sigma x minus sigma y. So you'll get that in degrees. And this is the plane of maximum principal stress. And the plane of maximum minimum principal stress will be 90 degree plus theta 1. Okay, so you have to visualize that from the Mohr circle diagram. So clear. So that is 121.72 degree. Similarly, maximum shear stress, we have the expression, and you can also determine the angle of maximum shear stress, right? That is minus 13.28 degree. So we have determined the principal planes and principal stresses and stresses on inclined planes. So this example, second example, is on the Mohr circle. This is a standard example since you already know the concept of Mohr circle, right? I have taken a standard example from a standard textbook, that is Mechanics of Materials by James M. Gray, which clearly explains step by step how to draw the Mohr circle. And since this is self-explanatory, so you can read on your own. Okay, so if you have any doubts, I will clarify during the live class. So I'll just push through the slides for a few minutes. So please read, it is explained thoroughly, and follow it. Try to draw on your own on a piece of paper, okay, so that you will get a feel of what Mohr circle is. We will use this more in this course, okay, and try to solve as many problems as possible from your MOS textbooks. So here they're explaining how to determine the center of the circle, right? So which is the average of sigma x and then sigma y. So first draw the sigma x1 axis and then tau axis. So tau, so it is shown at the bottom. Can you see at the bottom? Tau x1, y1 and sigma x1, the right axis. And sigma x1 is actually minus 50. So you have to go on the negative side. Okay. So mark it on the x-axis, and then you take the average of sigma x and sigma to locate the center, that is C. Fine. Then what about the radius? How do you determine the radius? At point at minus 50, you draw a vertical line whose magnitude is equal to 40 MPa. That is at point B or point A. Okay. So this is our plane actually. We are in this plane. Okay. We are in this plane. So theta equal to 0 is our plane. reference plane, first plane. That is minus 20 MPa situated from origin O. Origin O is also not here. So that is what they have kind of explained. So graphically, what you can do is now you can also draw the 40 units, 40 MPa on the negative y, that is tau direction, and connect point A and point B passing through C. So the radius of the circle is CA or CB. With C as center, you can draw the circle, right? So points P1 and P2 will give us the principal stress values, okay, and as well as the theta direction. With point A as theta equal to 0, you measure the angle, okay, for P1 and P2. What is the angle? That is what they have indicated. So P2 is actually 26.6 degree and P1 is actually 116.6 degree, okay. So analytically also you can calculate radius. We have the expression, that is what they have given, right? So what are the stresses on the inclined plane at theta equal to 45 degree? Yes, it's very easy. With AB as the reference, that is 0. From there you move by 45 degree in the counterclockwise direction, okay. Coordinates of point D. Coordinates of point D. So theta is equal to 45 degree, which means you have to move by 2 theta in the Mohr circle. That is what we have learned, right, in the video lecture, earlier video lecture. But actually it is theta equal to 45 degree plane. Graphically we have to go by 2 theta. So it is shown 90 degree. D and D prime. Right? So evaluate their coordinates. You will get the sigma normal stress. Right? What are the coordinates of D and D prime? You will get the values of sigma and then tau. Okay. So they have explained clearly here. It is 60 MPa and tau is 30 MPa. Right? So calculate the principal stresses represented by point P1 and P2 on the Mohr circle. So it is simply minus 20 plus 50, that is equal to 30 MPa. So likewise, you can go through, and maximum shear stress is also given, which is S1 and S2, right? Passing through the center, line passing through there. It is a diameter line. 50 MPa, obviously radius of the circle. And then you can represent it graphically like this, and you know how to do it as I have already explained. Okay. Then I think we are done. Thank you. These are the references I've used.